Welcome to the Capstone. Over the next 10 lessons, we'll build one complete machine learning project from scratch, a loan risk model for a bank. But before we touch a single model, we have to do the step beginners skip, framing the problem. What, exactly, are we predicting? Here's the situation. A bank lends money, and most borrowers pay it back. But some don't, they default, and every defaulted loan is money that walks out the door and never comes back. The bank wants that to stop. Now, lose less money is a fine goal for a meeting, but a model can't optimize it. There's no input, no target, and no single number to push up or down. Before we can build anything, we have to sharpen this into something precise. So start from the decision the bank actually makes. Every time a new applicant walks in, the bank must choose one of two things: approve the loan or decline it. That choice is what we want to support. A model doesn't make that choice directly. Its job is to predict the risk behind it, the probability that this particular applicant will default. That's a number between 0 and 1. Later, a threshold turns that probability into approve or decline. But will they default has to be defined precisely, or we can't label a single example. So we make a rule. Repaid on time is label 0. 90 or more days late is a default, label 1. Now default is a rule, not a feeling, and every past loan gets a clean 0 or 1. To learn, the model needs history, past applicants, the facts we knew about them, age, income, credit score, loan size, and crucially, what actually happened. Each row ends in an outcome: repaid or default. This labeled history is our training data. Here is that history: 500 past applicants from our dataset, 1 dot for each. Right now they all look the same. But we know how each story ended. Let's color the ones who defaulted red. Counting them up. 115 of the 500 defaulted. That's a base default rate of 23%. Remember that number, it's the ground every model stands on. Now, our model will sometimes be wrong, and there are two very different ways to be wrong. We can approve someone who then defaults, and lose the whole loan. Or we can decline someone who would have repaid, and lose only the profit we'd have earned. These are not equally bad. Let's put real prices on them. Say a bad approval cost the bank $5,000, while turning away a good customer costs $1,000. A bad approval hurts 5 times as much. That asymmetry is the heart of this whole project. We can lay all 4 outcomes out in a cost matrix. Approve someone who repays, no loss. Decline someone who default, no loss either, good call. But the two mistakes carry very different prices, -1,000 and -5,000. Here's why the usual scoreboard, accuracy, will mislead us. Imagine a lazy model that simply approves everyone. On our data it's right 77% of the time, because most people do repay. 77%, that looks fine. But follow the money. Approving everyone means approving all 115 defaulters, at $5,000 each. That's $575,000 lost. 77% accurate, and the single worst model we could ship. So the objective isn't to make the most correct guesses. It's to minimize the expected cost. Catching defaulters, recall, is what saves the most money. And the metric we optimize has to follow the business cost, not the other way around. There are also constraints a real lender must respect. The model has to be interpretable. By law, we may have to explain why someone was denied. It has to be fair, lending discrimination is regulated. And it has to be fast enough to decide in a fraction of a second. That's the frame. From here, 10 steps take us to a shipped model. Frame the problem, pin down the data and metric, explore, build an honest baseline, a pre-processing pipeline, compare models, tune the winner, evaluate on a sealed test set, analyze errors and fairness, and finally deploy and present. We are on step 1. So, the lesson before the machine learning. Turn a vague goal into a precise prediction. Define the target so every row can be labeled. Recognize that the two mistakes cost differently, and price them. And optimize expected cost, never blind accuracy. Next, we'll look hard at the data and choose our success metric.